Are you ready to learn about transformers? No, not that kind of transformer. These kind of transformers. You've probably seen this type. You've probably used this type around the house, sometimes plugging in different appliances. They come with these little boxes. Those are transformers. Some of you might have printers that have similar boxes, but then have a cord that goes to the wall. Those are transformers. And of course, all your cell phone chargers, which I know you're familiar with, are all transformers. You've probably also seen these or these hanging from telephone poles around your neighborhood. The only difference is here there's three separate ones and here's there's just one. Either one of them, either one works. These are all transformers. And some of you might have actually seen these around town, although Edison does a pretty good job of hiding these. They'll plant bushes around the outside of places where these are. Sometimes they'll even build walls or enclosures to keep you from seeing them. But those are transformers. And some of you who like to fiddle around inside of electronic appliances have probably noticed these guys inside there. Those are also transformers. They all do the same thing. And what is that thing? They convert voltage. That's what transformers are all about. They have to convert voltage. But why? Why does one want voltage converted? Well, for starters, usually where you make the electricity, let's say a big hydroelectric dam, or maybe out in the desert where there's they've got a photovoltaic farm or some other solar engine making electricity, or where they've got wind turbines, or where they've got geoelectric installations. Those places make electricity at a certain voltage. In this example with the dam, it's 120. Sorry, it's 24,000 volts. Okay. Well, we can use a transformer like this one to step that up. That's the term we use, step it up. In other words, convert it to 240,000 to 400,000 for transport. Why do we do that? Usually transport is on, when you see these big metal pylons, they're transporting electricity from a long distance away. It's just more efficient. There's less loss if you can ship it at a high voltage, and so they do that. Problem is, when it gets to town, you don't want it going around town at these high voltages, so that's where we have an electrical substation that drops it back down to, let's say, 24,000 volts, and that's what you find at the top of the wires at the top of the telephone poles. Those are 24,000 volts. Could be 40,000 volts too, somewhere in that neighborhood, but in the thousands, tens of thousands of volts. Then we need the other transformer, the ones that are hanging from the telephone wires, to drop it down to 120 volts to 240 volts to get when it comes to your house. Okay, how is that done? How do we do it? That's why we do it, by the way. And then you might have other transformers because the small appliance you have doesn't need 120 volts. Your phones certainly don't to recharge. And so it gets dropped down again. How is that done? Well, it uses the principles of electromagnetism, which we've been studying, and it converts the voltage. Two principles. They're related, but two principles. Here on the left side of the screen, we have a coil of wire with an iron core. Now what happens is if we run current through that coil, well, it's going to create an electromagnet. Reed did that. Remember I had you make electromagnets. You had a coil of wires and you had an iron core. Most of you used nails. Some of you had large screws, but same idea. It's an iron core, and you picked up paper clips. You created an electromagnet. Okay. Well, if we extend that iron core to the other side and have another core as our output, well, we got a magnetic field. And remember, if we have a moving magnetic field in a coil, we create current. So remember, had to do that too. And the only difference, whether you were going in and out, whether you got positive or negative current, and the faster you went, the more current you got, and so forth. But remember, it had to be moving. And so over on the left side here, we're using the idea of creating an electromagnet. We have current running in this coil, and we have an iron piece here, and the iron is becoming an electromagnet. Then over on this side, we also have a coil of wires, and we have an electromagnet in it, and so it's creating current coming out. Now you should be saying, well, wait a minute, this thing isn't moving. The electromagnet's not moving. It shouldn't be creating current, and you're correct, but it is moving. Let me tell you why. This input voltage is 72 volts AC. Way back at the beginning of talking about current electricity, I told you there were two types: direct current and alternating current. Direct current is what we get off of the batteries or out of those little boxes that you used, power boxes you used during the labs. That was direct current. But when you plug into the wall, you get alternating current. And what's the difference? Well, most of the things we learned about circuits applies whether it's direct current or alternating current, with some exceptions. But alternating current, what makes it alternating is that it's flipping back and forth between positive 72. So this one's going here, input is 72 volts, and it flips to negative 72 volts. And how often does it do that? Well, it does that 60 times every second. So you see this little wave drawing that's over here on the left side is indicating the wave that's created by this flipping back and forth from positive 72 volts to negative 72 volts. In fact, it does this 60 times every second. So that's like cycling a wave. And so we use the same terminology. It's the frequency. And in this case, it's 60 times every second. So it's 60. And do you remember the unit for that? That was hertz. Okay. We use the same terminology here, 60 hertz. Okay. So as it flips from positive to negative, the poles of the electromagnet that it's creating are also flipping. What was north becomes south, what was south becomes north. So it's flipping back and forth, north, south, north, south, north, south, north, south, 60 times every second. So it's doing that over here on the right side as well. And so we're flipping the magnet, the electromagnet's flipping back and forth, north, south, north, south, north, south, north, south. And so we do have a moving magnetic field, and the moving magnetic field is creating a current in the coil on the right side. And it's producing 504 volts. AC also, so it's going from positive 504 volts to, I left out the 4, to negative 504 volts. And it's doing it 60 times every second also, okay, just the same as this side. In fact, that's the one thing that Edison promises, is that this frequency will be 60 times every second. They don't promise when you plug into your 120 volt outlets it's 120 volts. It's just going to be somewhere between 100 and 130. That's all they're kind of promising. But they do stick to this 60 hertz. That is for sure always going to be 60 hertz. Okay, so let's take a look at a real one. Here's one. They don't all look like this. They're all different, but they do have, this one's got an iron core. It's got a coil on the left side. It's got a coil on the right side. There's a close-up here of the coils. So notice on the left, there's not as many coils as there are on the right. There's more coils on the right. So we're increasing the number of coils. So we're going to increase the voltage that you're going to get out of this. Okay, in this schematic, it's not too important that you see what's going on here, but notice this gray area is representing the iron core. The coils are represented by these lines around it. And notice here we've got a current coming in. The squiggly means it's AC. So this is our current source, and it's AC. That's what the squiggly wave-looking line it represents. And we got current coming in. We're going to have voltage across the two sides of this, and we're going to have the number, capital N for number, of coils. And then on the output side, we're going to have capital N sub S for the number of coils out, the voltage out, and the current out. Okay. Now, what do the P's and what do the S's mean? This is input. This is output. Why don't they use I and O? I don't know the reason for that, but they don't. They call the input the primary, and they call the output the secondary. So you're going to have to remember. So you're going to have to remember that P is primary, S is secondary. So this is just not a real transformer, it's just kind of an idealized diagram of one, where we have number of coils in, which would be the primary. So number primary, and the number secondary. We're going to have input or primary current, and we're going to have input voltage or primary voltage, and we're going to have output current or secondary current and output voltage or secondary voltage. And this is stepping up because look, the number of coils goes up in number, so the voltage is going to go up in number also. And of course we have step down transformers too, where we have here, look, the number of coils on the left is much greater than the number of coils on the right, and so the voltage is also going to be high on the primary and low on the secondary. So we're stepping down. The voltage is going down. Okay, and there's our real one again. So the ratio of the voltage in to the voltage out, or the primary voltage to the secondary voltage. Remember, primary, secondary, in, out, primary, secondary. The ratio of the voltage in and out is going to be the same as the ratio of the number of coils, capital N for number of coils, in, out, primary, secondary, primary, secondary. So you're going to have to remember that. Primary means input, secondary means output. Okay, and the ratio of the voltage in to the voltage out, or the primary voltage to the secondary voltage, is going to be the same ratio as the number of coils in to the number of coils out, or the primary number of coils to the secondary number of coils.
Example 1. A step-down transformer has a primary coil of 3,000 turns and a secondary coil of 200 turns. If it's plugged into a 120-volt power supply, what voltage will it supply? Okay, so we have a step-down transformer. That means the number of coils is going to go down and the voltage is going to go down. And it has a primary coil of 3,000 turns. That would be our NP for primary, or input, and that's 3,000. Okay, and our secondary coil has 200 turns. it's plugged into a 120 volt power supply. That means that's what it's getting. So that would be its voltage in or voltage primary. That's 120 volts. And we want the voltage secondary. Is what we're looking for. Okay. So this ratio has to be equal to this ratio. You could say 3000 is to 200 as 120 is to what? Well, it's going to be a smaller number. We can set up our ratio like this, and P is to NS as VP is to VS, and we're looking for VS. So I'm going to do this. I'm going to flip both of them over. And I'm going to multiply both sides by V sub P. That'll cancel, and I'll get V sub S is equal to N sub S times V sub P over N sub P. Okay? And now all we have to do is plug in our values. And that's going to be 200 times 120 volts divided by 3000. Okay, notice our only units we have left are volts, which is good because that's what we're looking for. And when we do this division and this multiplication and this division, we're going to get 8 volts. That's our answer. Example number 2. A step-up transformer used on a 120 volt line has 95 turns on the primary and outputs 3600 volts. What are the number of turns on its secondary coil? Well, it's a step up again, and we are definitely going from 120 to 3600 volts. And so the 95 is also going to have to increase to a bigger number. So volts on the primary is 120 volts. Volts on the secondary is 3600 volts. Number of turns on the primary is 95. What are the number of turns on the secondary? And again, the ratio of this to this has to be the same as the ratio of this to this, or this ratio has to be equal to this ratio. And we're looking for this. So I'm going to flip them over again. I'm going to have NS over NP is equal to VS over VP. I'm going to multiply both sides times N sub P to get this N sub S all by itself, which is what I want. It cancels. N sub S will be equal to, move up a little, V sub S times N sub P over V sub P. And when I put in values here, V sub S is 3600 volts, N sub P is 95, and V sub P is 120 volts. Notice volts cancels this time, and when I put all that in my calculator, I'm going to get 2850. It's not units, but we can call them turns, and that's our answer.
What about conservation of energy? Remember I told you that might be bothering you. And why isn't it a problem? Well, here's where the current works out. So notice the voltage, we have primary to secondary. Remember, that's input and output. And the number of coils, primary to secondary, input to output, equals the ratio of the current. But now it's secondary to primary. It's output to input. Why is it different than the other two? Well, that's where conservation of energy comes into this. Remember what power is, how to calculate power with electricity is voltage times current. And so the power is energy per time. So that's also going to be how I'm going to find my energy is going to be voltage times current. And so as the voltage goes up, the current goes down. And so in exactly the opposite direction. So this is because of conservation of energy. Because of conservation of energy, my current is going to be flipped over in ratio versus the other two. Okay? So keep that in mind. That's what all our three ratios look like. And of course, you can manipulate them any way you want to find out what's missing. And
let's try the first problem from the problem set. It has two parts, A and B. We'll do both. A step-up transformer has 95 turns on its primary coil and 2,000 turns on its secondary coil. The primary circuit is supplied with an effective AC voltage of 150 volts. And A wants to know what is the voltage on the secondary circuit. Let's go ahead and do that. So we have a step up. That means and it tells us that we have 50 turns on the primary, 50 turns on the primary, right there, and 2,000 turns on the secondary, right there. Okay, the primary circuit is supplied with an effective voltage of 150 volts. All right, and we want to know what the voltage is on the secondary. Okay, and again, the ratio of these to this has to be the same as the ratio of this to this. Okay, and so that is looks like this: NP over N sub S is equal to VP over V sub S. And I'm going to flip both of those over and get V sub S over V sub P, N sub S over N sub P. I'm going to multiply both sides by V sub P, and I get V sub S is equal to N sub S times V sub P over N sub P. And if we fit in everything there, it's 2,000 times 150 volts divided by 50. And so we put all that in our calculator. The only units we have left are volts. And we put all that in our calculator and we get 6,000. And I'm going to add that to what we know. And we'll do part 2. Let's go back and see what part 2 is. Part 2 says if the current in the secondary circuit is 0.24 amps, what's the current on the primary? So we can add to our what we know here as the current on the secondary is equal to 0.24 amps, and we want to know the current on the primary. Okay. We're looking for the current on the primary. All right, so let me just cover up this, and we'll work over here. Now, where the ratio of the turns primary to the turn secondary is the same as the voltage primary to the voltage secondary, the current is actually the other way around. So the current secondary is the current primary. So these three ratios all equal each other, but notice this is primary to secondary, primary, secondary, secondary to primary. Okay, and we're looking for this. Which one of these should we use? Well, we could use any one we want. It doesn't matter. but let's use the voltage one, since we just found that. Voltage primary to voltage secondary is equal to current secondary to current primary. And we found ourselves on the bottom again. Let's flip it over. Current primary to current secondary is equal to voltage secondary to voltage primary. And we're looking for that, so we're going to multiply both sides by I sub s. So I sub s times I sub s, that'll cancel. I sub p is equal to v sub s times I sub s over v sub p. And let's move up a little bit. And we have voltage secondary is 6,000. We found that in part A. The current secondary is 0.24 amps, and the voltage primary is 150 volts. And we are looking for the current primary. And notice volts cancels. All we have left is amps, which is good. That's the unit for current. And we stick all this in our calculator. We're going to get 9.6. Okay, I want you to remember, while you're doing the problems, you're going to be asked to work on power. You're going to be asked about electrical power. And remember, electrical power, P, is equal to voltage times current. If you're asked for the primary power, it's going to be the voltage primary times the current primary. And if you're asked for the secondary power, it's going to be the voltage secondary times the current secondary. Okay?